Now that we know the protocol that we're going to follow, we can start thinking about the actual QKD system. And remember, the task here is to be able to integrate this QKD system that we will build with mobile platforms like drones. And so this requires a system level analysis of the trade space between performance and size, weight, and power considerations. If we want to put our QKD system on a drone, we need to make sure that the system fits on the drone, that the drone can actually lift it, and that it can be powered by batteries on the drone. And so to do this, we follow this general structure for our QKD system. In most demonstrations use lasers to generate their quantum states. However, lasers are often require bulky temperature controllers and high amounts of power. Resonant cavity LEDs present themselves as an ideal candidate because they're small and require very little power while still outputting significant amounts of light. And that's the source that we use in our QKD system. FPGAs are great candidates for control systems because they actually are very lightweight. They can be very lightweight. They can also provide a high amount of processing power that's necessary to process the high amount of key material that's generated during these communication system experiments. And additionally, importantly, also FPGAs can actually generate nanosecond scale electrical pulses that are used to blink or pulse our LEDs at really high speeds and generate very small amounts of light in the single photon level. Additionally, to encode the information in the degree of the polarization degree of freedom of the photons, as I mentioned before, we use half-inch passive optics because they're readily available, and also because they have relatively low size and weight. And so this is kind of what the QKD system that we envision would look like. We have for our control systems, we have FPGAs on both Alice and Bob. On Alice's side, the FPGA, it's like I said, doing some work in generating these nanosecond scale pulses. On Bob's side, I'll talk about a little bit more in detail of what it does. But this is what we kind of envision for this system. And so in the next slides, I'll actually be talking about what each of these components is meant to do and in more detail, and how we actually put all of them together to build our QKD system. So as I mentioned before, the BB84 protocol, in the BB84 protocol, Alice needs to randomly generate strings of ones and zeros that she's going to send to Bob. And she also needs to randomly choose a basis in which to encode that information. To do this, Alice needs a true random source. And it turns out that the FPGA can actually generate true random numbers on demand using a technique called hybrid Boolean networks. And so this is one of the tasks that the FPGA does, is to do this randomization for Alice. And these hybrid Boolean networks have been shown to pass all of the NIST random number generator tests, which are essentially the gold standard for random number generators. Another task for the FPGA, as I mentioned before, is to generate these nanosecond scale electrical pulses that then that pulse our LEDs to generate light. And to do this, we used a series of phase lock loops, and by adding two outputs of that phase lock loop together, and by shifting them at a nanosecond level scale with a resolution of 78, actually picosecond level scale with a resolution of 78 picoseconds, we're actually able to on demand change the width of these pulses. And so that's another task for the FPGA. So for our source, as I mentioned before, we use this resonant cavity LEDs, which receive these nanosecond level electrical pulses from the FPGA. They blink and generate light. But one of the things that we need to consider is the fact that we need to be able to generate, three different kinds of states, right? We need for the decoy state protocol to work with multi-photon sources. That's what the decoy state protocol is. And so we need to generate a signal state that has a higher intensity, decoy state that has a lower intensity than the signal states, and then a vacuum state. So to do this, we actually built a custom printed circuit board that can actually that it's attached to the FPGA, which can switch between a high impedance signal and between a high impedance signal and the nanosecond level scale signal that I talked about earlier, and we can actually, by using two different resistors, one higher than the other. In this case, R1 is higher than R2. And by sending, for instance, an electrical pulse to the signal path through R1, we can generate a signal that has a mean photon number of 0.7. And by quickly switching between a high impedance pin, we can send the same electrical signal through R2 and generate a signal that has a mean photon number of 0.3. And so this is how we actually generate these decoy states that I talked about earlier, one with a higher intensity and one with a lower intensity. And so the next step is so after the LEDs generate light, this light needs to be introduced into some polarization setup to actually encode the information and the polarization degree of freedom of that photon. To do this, we needed to essentially couple the light of the LEDs into a fiber, in this case a single mode fiber. And essentially the goal was to couple this RC LED into this fixed focus collimator that you see all the way on the left. And to do this, we made this custom aluminum holders that were separated and attached by an O-ring. And by tightening and loosening the screws that attach these two aluminum holders, we can actually change the angle of incidence into that fixed focus collimator to maximize the light that is coupled into that fixed focus collimator, which is then attached to single mode fibers on the left side there. And so everything I've covered so far can be seen in this picture. We use the FPGA to generate this nanosecond level scale pulses. We also use the FPGA to generate the random numbers that we require for the BB84 protocol. Additionally, we need this printed circuit board that connects the LEDs to the FPGA to generate those decoy states that I mentioned earlier. And then those LEDs are connected to a single mode fiber that you see all the way on the left there by using these custom-made aluminum holders that I talked about earlier. So this is the system so far, and this is how it's actually put together. And you can see those fibers then go somewhere, and that somewhere is actually the encoder, which is the next step in the QKD system, or the next item, or the next component of the QKD system on Alice's side. And so those fibers that you saw before come in where you see these arrows over here that say LED light. That's where the LED light actually comes into those fibers. We then use a combination of serial polarizer, mirrors, and quarter wave plates, and polarizing and non-polarizing beam splitters to generate our states. Typically, in BB84 protocol, you need 4 states to do QKD. 2 states coming from one basis and 2 from another basis. And in our case, as I mentioned earlier, we're using the circular basis and the rectilinear basis. So in theory, we would need the to generate the left circular polarization, right circular polarization, horizontal polarization, and the vertical polarization. But it turns out that sending 3 states but measuring all 4 can give you the same key rates as sending 4. And so we only generate 3 states. This allows us to save some space and also some weight in our system. And so the 3 states that we generate are left, right, and horizontal in our system. We then send these 3 states over free space to Bob, who then measures all 4 states, not just the 3 that we sent. So this is a key part of the protocol. So this is how the encoder actually works. And remember, the FPGA is actually able to choose which LED is blinking, and that's how we generate these states at random. Okay. All right. So that's actually everything that covers all of the components that make up Alice's setup. The control system, which I mentioned before, is the FPGA, the QKD source, which are resonant cavity LEDs, and the encoder, which is made up of half-inch free space optics. And I talked about how we actually integrate this system. So that's Alice done. Now we can talk about how what Bob does. As I mentioned, the quantum channel in our case is free space. Those three states, all L, R, and H, are all sent through free space to Bob. And so now for Bob, on Bob's side, there's a similar setup for the decoder, where we use, instead of using half-inch optics, we use one-inch optics to maximize the collection of light on Bob's side. So on Bob's side, he randomly chooses in which bases he's going to measure passively by using a beam splitter that you see here on the bottom right. That chooses whether the incoming photon will be measured in the rectilinear basis or in the left and the circular basis. And by using, again, a series of quarter wave plates and some beam splitters and mirrors, we're actually able to sort the information as it comes in. You can see that after the light is sorted, it is coupled into another fiber, into 4 fibers in this case, H, L, R, and V, which are then connected to a detector, as you can see in this image here, from right to left. So, from left to right. So the incoming light is sorted by the optics. Then the light is coupled into 4 fibers, which are connected to a single photon detector. The detector then generates electrical pulses that are then time tagged using the FPGA. And then the FPGA stores this data for later post-processing. And so this is actually the entire QKD system for Alice and Bob. And in practice, all you need to do is put it together in free space. And we do this by setting them on an optical table and putting and aligning them to each other using some mirrors. And we do this at a distance of about 1.5 meters. We then run our experiment, and we're able to collect data on Bob's side. And what does that actually look like? Well, this is what the data actually looks like in theory, not in theory, in the experiment. And what you see here, I'm going to talk about the plot a little bit. What you see here is the average counts that you get in each of the detectors: left, right, horizontal, and vertical. And this is kind of like this is the average counts rate on the y-axis and time. So we collect data for about 100 seconds, and these are the average counts. So you can see that we get a decent amount of counts on each channel. And these drops and counts that you see are actually done intentionally. Because there is large amounts of data being generated on the FPGA, we need some time for the FPGA to actually save this data. And so we intentionally stop sending states during a period of time that's 0.5 seconds for the FPGA to process all of the data that came before that. And then once it's done, we pick it back up, and that's why you see these drops and counts here. They're done intentionally. And so this is what the data actually looks like. But what do we do with that data? What happens once you do the QKD exchange? Well, when you're doing quantum key distribution, the QKD exchange is only the first part of the whole protocol. You then have to do some what's called information reconciliation. So some Kuber calculations in our case. We need to calculate the Kuber of the key that we exchanged. That allows us to calculate the raw key as well. And remember before that we are aiming for a Kuber that is below 11%. And in our system, you see here that our Kubers are well below that threshold, and therefore we should be able to get a secure key out of our system. After you do these calculations, you need to actually put it put your key through security analysis. For example, you need to do error correction, privacy amplification to get as an actual secure key that can be used by Alice and Bob. We don't do this on our side. The security analysis is actually done by Norbert Lukenhaus's group at the University of Waterloo. They essentially spearheaded they're the world leads in doing a security analysis. Specifically, Lars Kamen was able to generate a model specifically for our system to do security analysis and get a secure key out of our system. And they did this, and we were actually able to get a secure key that is 41.3 kilobits per second on our tabletop experiment. So it works. This experiment shows that our QKD system is viable and that it works. But is it actually something that can be integrated with mobile platforms, which is the goal that we set out to achieve? And the answer is yes. But for field application, there's something that you have to take into consideration. In the lab, it's easy to keep Alice and Bob aligned to each other, right? Because on an optical table, there's barely any vibrations, there's no swaying. Whereas if you were to put them, for example, on a drone, there's going to be a lot of vibrations, there's going to be a lot of swaying, and there's going to be wild temperature changes sometimes if you do it at night. And so these are all things that you need to be able to overcome if you want to do quantum key distribution with these mobile platforms. And so the first task that we need to solve if we want to integrate our QKD system, which it's small and it's well packaged, so that it can be put in these platforms. So the first task is to actually be able to keep Alice and Bob aligned to each other at all times, and we do this by implementing a pointing and tracking system that has two levels of essentially alignment. One of them is coarse alignment, and is done using this method of putting the QKD systems on these professionally graded gimbals that are attached to a drone in this case. And these gimbals can actually move these QKD platforms and try to keep them aligned to each other at all times. And we do this by placing an IR beacon and an IR camera on both sides. And for example, the IR camera on Alice's side will take a picture of the IR beacon on Bob's side, and that's what the images you see here are of. They're images of that IR beacon. And that gives you a blob. And by looking at the centroid of that blob, we can use that along with a Raspberry Pi to have a feedback loop and say, okay, make a certain amount of corrections to go to the target that you want to be at. And on Bob's side, it does the same thing. And they try to, they are continually trying to look at each other using this system. We use a PAD control loop to do this, and we're able to get a resolution of 0.025 degrees, and we do this at 50 hertz. We do these corrections at 50 hertz. In addition to the coarse control loop, we also do a fine control loop, and this one is a little bit more involved. In this control loop, we align Alice's signal, so the quantum signal from Alice, with in this case, if we go from left to right, so we align Alice's signal with a 520 nanometer laser by using a dichroic mirror. We align them to each other, and then we send that signal through two fast steering mirrors labeled FSM here. These fast steering mirrors are able to be controlled by the Raspberry Pi, and they're able to move and change the direction of the now combined quantum signal and the 520 nanometer laser. It goes through free space to Bob, who receives this signal using also fast steering mirrors on his side. That signal is then split using another dichroic mirror that lets the quantum signal through to Bob, but reflects the laser signal to a positioning sensing diode, PSD in this case, which looks at the location of that laser. And by setting a target location on that laser, we're able to do a feedback loop with the Raspberry Pi and the fast steering mirrors to move that laser signal to the position that we want. And we set that position in such that when the position is acquired, that Bob is receiving a maximal amount of signal from Alice. So in short, what that means is that if the laser is aligned to the PSD position, then Bob is aligned to Alice. That's essentially what that means. We have a similar loop going to the left with a 705 nanometer laser, and that also goes to a PSD on Alice's side, and we do a same feedback control loop. This loop actually allows us to get a performance or a resolution of 0.001 degrees on this alignment procedure, and we do these corrections at 800 hertz. And so this actually, and so the way this works is that we use the coarse control loop to try to get like our first signal on Bob and Alice, and then we use the fine control loop to maximize that signal and to keep them aligned when they're vibrating and swaying